Everyone, so this is the video for the Matlab component of homework 4, and in this homework you're going to be replicating some figures from this paper which looks at different emergency response strategies to a smallpox attack. So it specifically looks at 3 strategies. The first is trace vaccination, which is when you isolate the people who are symptomatic and then find all of their contacts and just vaccinate those people. And then the second is mass vaccination, which we refer to as MV, and that's where as soon as the epidemic starts, you just vaccinate everyone. And then the last is the CDC policy, and for the purposes of this model, the way it works is that they initially start with TB or trace vaccination, and then on day 28 they switch to MV. So we're going to model these different vaccination strategies and determine which one is the best. So now we're going to move to the Matlab template code, and just before we start, I would highly recommend reading through the paper before starting the homework and maybe before watching the video, because it gives a lot of the context for this and describes the model that we're going to use. And the first thing we're going to do in the code is set all of the parameters for all of the constants in the model, and those are all described for you here in table 1. So it explains what they all are, and then these are the values that you should be inputting into your code. And then the next thing we're going to do is, it says solve ODEs for phase 1. So phase 1 goes from day 0 to day 5, and if you read the paper, they say that on day 5 is when they initiate either trace vaccination or mass vaccination. So in phase 1, people are just getting infected, but there's not actually any vaccination strategy happening yet. And if we go down to the bottom, your ODEs for phase 1 have already been implemented in the code for you. And if you look down here, these are the 7 variables for the phase 1 ODEs. And so you need to, in your ODE solver, set the initial conditions for these 7 variables, and then these are the 7 ODEs corresponding to each of those variables, and your ODE solver is going to give you an output that corresponds to the value of these 7 variables over time. So the first one is S0, which is the number of susceptibles. Again, these are all the same as the letters that are used in the paper. So if you're confused about what different variables correspond to in the code, I would again look at the paper. So I01 corresponds to the number of untraced individuals in stage 1, and then stage 2, stage 3, and stage 4. So stage 1 through 4 correspond to the different stages of the infection, and again, those are described in the paper, what each of those are. And so in phase 1, we only care about untraced individuals because nobody's been traced yet because the vaccination hasn't started. So that's why we're only concerned with these 4 variables for the number of infected individuals. And then Z corresponds to the number immune from previous vaccination or recovered, and then D is the number dead. So just to give a couple of hints about the initial conditions, initially in phase 1, everyone in the population is susceptible, and there's a parameter that we defined above that represents that number. And then for the number of untraced individuals in stage 1 of the infection, there's also an initial parameter that we defined above for that, and then we're assuming nobody is yet infected in stages 2 through 4, and that nobody is immune from a previous vaccination or dead yet. So going back to solving the ODEs for phase 1, you guys should be pretty familiar with the ODE solver at this point, but here is where you're going to call the function that has your ODEs, which we were just looking at below, and then here you're going to put your T-span, which, as a reminder, phase 1 goes from day 0 to day 5, so that should give you a clue as to what your t-span should be. And then here you're going to put the initial conditions, and then which we just talked about, and then here's just an empty vector, and then theta has already been described for you that has all of your parameters. So after you've run your ODE solver, you're going to want to unpack Y, which is going to have 7 columns corresponding to the 7 different variables and their values over time from day 0 to day 5. So you're going to want to unpack those columns, and then I would recommend solving for the total infected over time. So that would be your values for I01 plus I01 plus I02 plus I03 plus I04. So it's just the sum of all the people infected in the 4 different stages, and that will be helpful to use later. And then also for the next phase, phase 2, in which we start one of the vaccination strategies, you're going to need initial conditions which correspond to the final conditions of phase 1. So it's also a good idea to save the final values of all the 7 variables at the last time point in phase 1. So the next part of the code has you solve for the phase 2 ODEs, and we're first going to be looking at the trace vaccination case. So in the paper they go out with the model to 300 days, and we've already done a 5-day phase 1. So as a hint for your t-span for phase 2, we're going to do 295 days. So going down to the phase 2 ODs, we now have a lot more variables. So we have 17 variables here because now people are being vaccinated, so that introduces more variables into the system. So I already talked about what S0 and I0 1, 2, 3, and 4 are, but there's some new ones here that we didn't have in phase 1. So again, these are all in the paper, but Q0 is the number of people in the queue who are susceptible. So the queue is people who are waiting to be vaccinated. Q1 is people in the queue who are in stage 1 of the infection, and then stage 2 and stage 3. By the time you're in stage 4, you're not getting vaccinated. And then H corresponds to the number in febrile quarantine. So they discuss in the paper that those in a fraction of people in stage 3, when they go to be vaccinated, are determined to be febrile and then are put into quarantine. And then S1 is the number of susceptibles who have been traced and vaccinated. And then I11, this is similar to these variables, but this is the number of traced and vaccinated people who are in stage 1 of the infection, the same number in stage 2, stage 3, and stage 4, and then we already talked about Z and D. So for phase 2, you're going to have to set the initial conditions for all of these 17 variables, and then your output for the ODE solver will again be all of these variables over time for from the 0 to 295 days, which corresponds to 5 to 300 days in the overall model when you also include phase 1. So for initializing these variables, like I mentioned before, you're going to want to use the final states from phase 1 for all of the variables that we solved for in phase 1. So that would be these 5 variables as well as Z and D. And then the rest of the variables we're going to assume to just be 0 because initially nobody's been vaccinated yet, so we don't have anyone in the queue, we don't have anyone in quarantine yet, and nobody's been vaccinated or traced, so these are all 0. Okay, so once you've initialized all your variables and run your ODE solver, you're going to want to save some of these variables for plotting purposes. So first, similar to what I suggested for phase 1, you want to create an array that has the total number of infected people over time for phase 2, and then you're also going to want to create a vector that has the total number in the queue over time for phase 2. Okay, and then what you're going to do here is you want to combine your values from phase 1 and phase 2 to create arrays that have the variables you're interested in for plotting over time for all 300 days. So that's why here you're creating an array that has spaces for L1, which corresponds to all the time points in phase 1, and then L2, which corresponds to all the time points in phase 2. And I would actually recommend creating 4 arrays. So the first array would have all your time points, the second array would have the total infected over time, and then the third would have total in queue over time. I'm not sure if I just spelled queue right. And then the last would have the total dead. Okay, and the way you're going to want to do this here is to loop over first all the time points in phase 1, so that's from 1 to L1, and for each time point you're going to add the specific value to your array. So for the time variable, you're just going to want all of the time points from phase 1. Then for the infected, you're going to want to add the total number of infected for each time point, which you should have, as I suggested, created an array that had the total number of infected for each time point from phase 1. So you can call that here. And then for your total in the queue, there's no one in the queue for phase 1, so you don't need to add anything. That will just be 0 for all of the phase 1 time points. And then similarly, you're going to add the value for total dead. And then you're going to do the same exact thing for phase 2. And then at the end, you should have 4 arrays that correspond to the time points, the total number of infected, and the total in the queue and total dead for each of those time points for trace vaccination. And then this is going to be helpful for plotting. And I should just mention, so the reason you have +5 here is this line is showing you an example of, this is how you would input the time points for phase 2 into your array. So you're going to do n because you're going, that's the time point in phase 2 that you want, but you want to add it to n plus L1 since you already have all these points from phase 1. So you want to add your new time points from phase 2 after the phase 1 time points. And then you're adding 5 because your phase 2 is going to go from 0 to 295, but you want to add 5 to that because you actually should be going from 5 to 300 if you consider the full model with the phase 1 at the beginning. And then you're similarly going to add the values for the other 3 arrays. So the next thing we're going to do is solve for the mass vaccination strategy. So your phase 1 is exactly the same, so we're just going to solve the ODEs for phase 2 for the mass vaccination case. So the ODEs are the same as they were before, but now the initial conditions are going to change. So essentially everyone from phase 1 who was in S0, or who was in the susceptible unvaccinated case, is going to go straight into the queue at Q0. And everyone who was infected in stage 1 is going to go straight into the queue for, in the Q1 variable, etc. And then the only people who aren't going into the queue are people in stage 4 because once you're in stage 4, you cannot be vaccinated. And then here where we set theta 10 to 200, this is the service rate, so it's the number of people per day that can be vaccinated, and this becomes much higher for the max vaccination case because people don't have to be like located as they had to be with the trace vaccination strategy. And then once you solve your ODs, you're going to want to do the same thing that we did above, where you create these arrays that have all of the values for the time points, the number infected, number in queue, and number dead from 0 to 300 days. So you're going to do essentially the same exact thing, but for your phase 2 data, you're going to add the data from the max vaccination case instead of the trace vaccination. Okay, so at this point, you are going to be ready for plotting. So you're going to be replicating figure 1A and B from the paper. So this is showing the number in the queue and the number infected over time from 0 to 300 days. This is for the trace vaccination case, and this is for the mass vaccination case. So now at this point you have all of the data to make these plots. So here most of the code is written out for you, but basically y1 is going to be the number in the queue for first. You'll do this for the trace vaccination case, and then your y2 will be the number infected, and you set up these arrays here that have the number of infected and the number in the queue for each time point from 0 to 300 days. So you're just going to plot those. And then you're going to do the same exact thing for the mass vaccination strategy in a separate figure. Okay, the next thing you're going to do is compare the death rate for TV, MV, and the CDC policy. And for the purposes of this, we're going to assume that the CDC policy is to switch from TV to MV on day 28. So phase 1 is the same as what we already solved for, but then for these are going to be solving for the CDC policy. So you're basically going to have two segments of your phase 2. So the first this is going to be TV from day 5 to day 28. So you're going to use basically the same like initial conditions you used for your TV for solving for TV above, but it's only going to go to day 28. And then here you're going to solve for MV from day 28 to 300. Yeah, just remember that the initial conditions for this ODE solver will correspond to your final conditions from the first component of phase 2, which was TV. And remember that the people who are infected go straight into the queue when you're doing your initial conditions. Okay, and then you're going to want to do a similar thing to what you did above, where you create an array that has the number dead over time for phase 1, followed by TV phase 2, and then MV phase 2. So you can use a very similar loop to what you did above, except you already should have all of the number dead over time for phase 1. And then you're going to plot the number dead so this would be for TV, then plot it for MV, and then for the CDC policy. And then you can compare basically which policy is the best at reducing the number of deaths. So the last thing you're going to do is a sensitivity analysis, which is what they did in figure 2 of the paper. So this is basically a way of looking at how sensitive the model is to changes in a certain parameter. So here they're looking at how changing different parameters affects the number of deaths in both the TV and MV case. So in 2A, they're looking at when we vary the fraction of population initially infected from like 0 to, here they're doing it to 10 to the times 10 to the negative third, how does that affect the final number of deaths? And then they did the same for 3 other parameters. And so in the code, you're going to basically make this graph and then you're going to choose one of these three to do a sensitivity analysis on as well. So I'm just going to go through a really simple example of what a sensitivity analysis would look like. So in this example, I have my ODE set up here. So I just have one really simple ODE. So obviously you wouldn't actually need an ODE solver to solve this, but just for the sake of the example, we're going to use it. So the ODE here is dy dt equals a times y minus 3. So the only parameter that we have here is a, which is some constant. So what we're going to do up here in this function is vary a, and then look at what the final values of y are for all the different values of a. So how does changing a change the final value of y? So this is all kind of arbitrary, but for the ODE solver I need to set my t-span, so I'm going to set it for this to go from t equals 0 to t equals 0.1, and then I'm going to kind of arbitrarily set my initial condition to be that y equals 1 at t equals 0. And then I'm going to just create a vector to store all my y values in. So I'm gonna, or first I should set my a values. So I'm gonna test values of a going from 1 to 50. So I'm just creating a vector that has all my a values, which are it's just a vector going from 1 to 50. And then I'm going to make an empty vector for my y values, so I'm making it 50 long so that we can store, for all 50 values of a, we'll store the value of y. Okay, and then the next thing I'm going to do is I'm going to make a for loop, and for each value of a, I'm going to run the ODE solver and determine the final value of y. So I'm going to say for n equals 1 to 50, and then I'm going to say the specific a value is going to be a vals n, and then I'm going to run the ODE solver. So I'll say ty equals ODE 23s at, I'm going to call my function, which is just called example, t-span init, and then a value, because I only have one parameter, so I'm just going to put that one parameter into my ODE solver, and then I'll say L naught equals length of t, and then I'll store the value of a, y vals n equals y of L naught. So this is basically going to put into y, the vector y vals, the value of y at the final time point, so at t equals 0.1. And then end the for loop, and then we can plot this. So similarly to what we saw in the graphs in the paper, we're going to plot on the x-axis the parameter that we're changing, so in this case it's a, and then on the y-axis we'll plot the parameter that we're interested in seeing like the effect of. So here we're going to plot y in the case of the sensitivity analyses in the paper. On the y-axis you're plotting the number of deaths because that's what you're interested in seeing the effect on. So here we're going to plot a vals and y vals. So I'm on the y-axis, it's value of y at t equals 0.1, and okay, so I'm just gonna run that, and then, oops. Oh, sorry, had a typo. Okay. Okay, so it worked that time. So on the x-axis, we have the different values of a that we tested ranging from 1 to 50, and then for each value of a, it shows us what the value of y is. So obviously, for this ODE and for the conditions that we're looking at, the y is pretty sensitive to the value of a. So going back to our template code, we're going to do something pretty similar to what we just did in the example, where we're going to make a for loop where in each iteration of the loop we have a different fraction of population initially infected, and then we're going to run the ODE solver and determine the final number of people dead, and then we can plot the number dead versus the fraction of the population that was initially infected. So just to go through a little bit of this code, you're going to basically be replicating this figure, so you're going to want to solve for the TV case as well as the MV case. So in dead, this vector, you can store the final values of the number of dead for each of the different fractions for the TV case, and then here you can store your values for the MV case. So initially, you first want to solve for your phase 1, for the phase 1, and you don't need to store these values. This is just to get your initial conditions for phase 2. And so then here, you're going to solve for the phase 2 with TV, and then here you're going to solve for phase 2 with MV, and this should be really similar to what you did above. And then here you can plot both, and you should get something very similar to figure 2a. So finally, you're going to do a second sensitivity analysis where you vary a different parameter of your choosing. There are the 3 others that they varied in figure 2 of the paper that you can choose from. And that's it. Good luck with the homework.